Welcome to another podcast. In this episode, we're going to be taking a look at what are called optimization problems. Essentially, an optimization problem is a problem that seeks to find the maximum or minimum of some value subject to some other sort of constraint. Usually, they're functions of multiple variables. And so as we're looking through this problem, we're going to try to use the constraint to solve for one of the variables. This is going to be the first of two problems that we look at. And so let's just go ahead and read through the problem, get some familiarity with it, and then we'll try to draw a diagram of it and go from there. So let's suppose we're trying to build a parking lot, and we're going to fence it in adjacent to a building that's already existing. Suppose we have 500 feet of fencing available, and because the building is one side of the parking lot, we're only going to need to fence in the other three sides. So I want to determine the dimensions of the lot that give a maximum area. So one of the best things that you can do here is actually start by going in and creating the diagram of the situation itself. So what I like to do is I like to start with a picture. So let's suppose that this is the building lot, and we're going to fence in. I'll do this in a different color. We're going to try to fence this in. So we'll have a piece here, and we'll have a piece here, and then we'll connect them. So I need to. All right, so there's our parking lot. So this is the building up here. And we've got the lot down here, and I need to introduce some notation. So I'm going to introduce the notation y corresponding to the length. And I'm going to introduce the notation x, which will correspond to the width. Then the other thing that I know is that the area of this lot is going to be equal to x times y. I know that the perimeter of this lot is going to be x plus 2y. So I have all of the information I need in order to try to figure out what is the maximum area I can have subject to only having 500 feet of fencing. Keep in mind, since it's length times width, that's where we get the x times y for the area. And because I'm not using the building side, I only need to have one x and then two y lengths for the perimeter. So the way that we typically write the problem is we'll want to say I want to maximize the function a, which is a function of two variables, x and y. So maximize the area subject to the constraint, and the constraint here is on the perimeter. The perimeter, x plus 2y, needs to be less than or equal to 500. So we're usually going to say that it's equal to, in other words, we're going to use up all of the fencing, but realistically, we need x plus 2y to be less than or equal to 500 feet. Now, the easiest way to go about finding this particular problem is to use the constraint. So I'm going to use the fact that x plus 2y equals 500. I'm going to use up all of the fencing to solve for the variable x. So we're going to have x is 500 minus 2y. And what that will allow me to do is it'll allow me to take the area function and replace x, so this is x times y, replace the x with 500 minus 2y. So we have 500 minus 2y, which is 500y minus 2y squared, and so now I have the area written as a function of y. Since this is a function of one variable, I can then find the maximum value of y to maximize the area. To do this requires calculus, or at least the way we've been learning it, it's going to require calculus. So I'm going to calculate the derivative of the area with respect to y. And so that's going to be, actually let me go ahead and use a different notation here. So I'm going to calculate the derivative of the area with respect to y. And that's going to be 500 minus 4y. And I need to make that 0. So I'm looking for a critical point here. So if I solve 500 minus 4y equal to 0, then I'm going to get y is 125 feet. So this is the optimal size for the length. Y needs to be 125 feet in order to give or to provide a maximum length. So what does x have to be? Well, we have x from this formula here. And so if we use that, then we know that x is 500 minus 2 times y, but the maximal y is 125. And if I plug that in, I get 250 feet as being the corresponding maximal x. And so we know that x is 250 feet wide and y is 125 feet. This means that with dimensions, so this is kind of finishing off the problem here, with dimensions of 250 by 125, the parking lot has a maximal area of 250 times 125, length times width, and that area that we think is the maximum is 31,250 feet squared. So that's what we think is the maximal area. Are there any other possibilities? Well, I need to, and I'm going to go in a different color and do this, I need to talk a little bit more about some things that are sort of lying in the background here that you may have overlooked. If I look at the area function, so if I look at my area function in terms of y, then my area function has some natural bounds here. In terms of y has to be between 0 and 250. Now you might ask, why is that? Well, if you look here, y equal to 0 makes the area 0, and y equal to 250 also makes the area 0 from in there. But that's not necessarily the reason why these are the physical bounds. If you think about a building built corresponding to a y value of 0, then it has no length, it's all width. And so we're looking at sort of the limiting case of having an x equal to 500 and a y equal to 0. That's one possibility. The other extreme is that I have a y of 250, which means that it's all length and it's no width. So it's all length, in which case I have a pin that looks like that, and so y is 250 on each side, right? So that's the 500 of fencing, and I have no width. So these are sort of like the limiting values. And the restrictions that are placed upon by the constraint, but also by the physical situation. And because of that, I'm trying to maximize a function, trying to maximize the area function on the interval from 0 to 250. And what we've learned in class is if I'm going to have a maximum, it's going to occur either at a critical point, which we found the critical point 125, or it's going to occur at an endpoint. So it is very, very important that you make sure you go back and check the endpoints as well. So this is the area function, but it's the area function that corresponds to specifically a value of 250, 125. So if I have 250 for x and 125 for y, that's the value I get. What if I have a value of, let's take the first case where x is 500 and y is 0. Well, the area in that case is 500 times 0, or 0. Okay, let's take the other extreme where I have a y value of 250, so the x is 0 and the y value is 250. Well, in that case, you also get 0. So the point is that these are not maximums, but they could have been. So we need to be very careful about that. Always keep in mind the idea of an absolute max, because that's what we're hunting for. And the absolute max here turns out to be with a y length of 125 and an x width of 250. So the maximal area is 31,250 feet for this example. Don't forget to check the endpoints of your intervals as well when we have problems that involve endpoints. The next example we're going to do doesn't have endpoints, and so once I find the critical point, I'm done. You could also use the first derivative test to test that this is indeed a maximum by showing to the left of this point for y and to the right of this point for y. You get increasing to decreasing. So that's one way of doing it, but it's pretty clear here that this is indeed a maximum. All right, thank you for watching.